Okay, welcome to part 2 of the vodcasts on potential dividers, itself part of topic 5. So in the last part we just introduced the basic potential divider circuit, which is a great circuit, it's very useful. If you know you're going to have an input voltage of one particular potential difference and you want another one. And if nothing's going to change, if that's just a question of controlling a supply, you don't have maybe much of a choice of what supply you have to be using this, but you know you want a particular output for the rest of your circuit, then you can set up a simple potential divider using the two resistors, no problem. But that's not everything it can do. We can also look at varying or using these circuits to control based on external criteria or stimulus. Now, I'm not talking about sophisticated digital electronics here. I'm talking about basic analog electronics, basic sensor electronics. So when we say sensor, we're talking about something which senses its environment and changes. And the change in this case would be a change in the resistance of a device. There are many of these, and here are 3 of them. We have a thermistor, which we've looked at before, whose resistance decreases when the temperature increases. We have a light-dependent resistor, which is also a semiconductor resistor whose resistance decreases, this time with increasing light levels. And slightly different, because it doesn't use semiconductors really, is a strain gauge, which is just very, very thin metal wire. You've got an example here. And if the wire, if the gauge itself stretches or flexes, then that changes the length of that wire, which changes the resistance. So in the case of wanting to use one of these circuits, then we basically replace the R2 from our previous circuit with the thermistor, light-dependent resistor, etc. Here we've got an example, and we've got the terminals that we showed before, but now we're actually putting a component here in the electronic switch. So the details of this component do not interest us. All that we care about is that it's a switch to turn something on, it turns a light on. Okay, and it turns a light on when the output voltage is 5 volts or greater. And we've done some tests, and we know that we want it to turn on when the resistance of the LDR rises to 200 kilo ohms. We can say it's got a range. A typical range for a light-dependent resistor might be close to 0, a couple of hundred ohms, up to 1 mega ohm, 1 million ohms. Okay, so we'll say at 200,000 ohms, at that brightness which gives that particular resistance, we want 5 volts to be output and our switch to turn on, in which case, what do we want R1 to be? We know the input is 12, output is 5, we know that R2 is 200 kilo ohms, so we've got our equation. We can rearrange our equation to give R1, and we can give a value of 280 kilo ohms. We can keep our calculations in kilo ohms if we want, as long as we are consistent. So let's just look at that more holistically. So that's the circuit that we've just built, with R1 being a 280 kilo ohm resistor. R2 with its resistance of 200 kilo ohms, 12 volt input gives us an output of 5 volts. Okay. If we were to do this in bright light, okay, in bright light we would have only 500 ohms on R2, then the proportion of the total is going to be much smaller, and therefore the out will be much smaller. In this case, 0.02 volts, therefore the switch will not turn on, the light will not light. If, say, it gets even darker, what's the darkest it can possibly get, pitch black, then the resistance of R2 will go up to 1 mega ohm, which is 1,000 kilo ohms, and V out will be, well, a much greater proportion of the total input. If we do the sums, it works out to 9.38 volts, which is, again, more than enough to turn the switch on. So that's an example of a sensor being used to control, a sensor with a potential divider being used to control a circuit.